Yes, sir. Good morning, sir.
Good morning. Am I audible?
Yes, sir. Quite clear.
My screen is visible to everybody?
Yes, sir. Yes, sir. Yes, sir.
Okay, okay. Good morning, everybody. Hello. Good morning,
Good
everybody.
morning. Good morning, sir.
Good morning. So, sorry being late. My system hanged in between. I have to restart the meeting again. Okay. So, so I will start my first lecture. It is basically the basic concept of mechanical vibration. As you know, vibration is a universal phenomena and it will exist in many forms and it will basically encompasses entire universe. You have seen the vibration phenomena in various form, like you can say uh, musical instruments, hearing, and so on. And in mechanical system, it is very much prevalent. So the we are having a few scientists and engineers who have responsible for the development of this field. So number one, we are having a astronomer. These fellow have studied the motion of celestial body in their orbit under some perception, and major astronomer who are basically pioneer in this field in the development of the vibrations are Copernicus and Kepler. And then we are having a physics scientist who have joined this astronomer, and namely Newton's and Rayleigh were the pioneer besides many others, and they have basically laid down the foundation of vibration dynamics. Then we are having a mathematicians who have basically laid the foundation of analytical dynamics. And the major mathematicians are Lagrangian, Euler's, and Hamilton's, besides many others. Then we have the engineers. And engineers have joined this band of scientists and astronomers, and they have designed and constructed the machines and the structures. And the pioneer engineers were Timoshenko and Dan Hartog. So these are the various personalities who have developed the mechanical vibration in general uh, to the current status. So from above you can say that vibration is a highly interdisciplinary area where engineering practices, physics principles, and mathematical theories are combined, and engineers, physics scientists, and mathematicians meet and interact in a closed loop. So in this subject we will take the view of engineering for the vibrations. So I will be applying the vibration concept to the mechanical systems as the course indicates. So basically mechanical vibrations are nothing but they are the vibrations executed by mechanical system. And you already studied the mechanical system definition. As per the mechanical system definition, it is a body or a system made of interconnected elastic elements, and these elements are constrained to move one another in a predetermined manner from input stage to output stage. That definition you already studied in theory of machine, that a machine should have a constrained motion from input stage to output stage, and that motion is predetermined, and then only then machine is helpful to human mankind. So let us come to the some more basic concept. As I already told you that you must know the 3 or 4 subjects very thoroughly, starting from the engineering mechanics, then strength of material, mechanics of material, and theory of machines. All these subjects will be very useful to understand this mechanical vibration course. So now let us discuss about the equilibrium conditions. Basically, you can have 3 equilibrium conditions. Number one, stable. Number two, neutral. Number three, unstable. So I will be discussing when you can have a mechanical vibration in a system. So, in the stable equilibrium condition, this P represents the lowest point on the cylindrical path, and suppose the cylinder revolves or rolls about the cylindrical path without slipping, then you can define the displacement of this cylinder by angle phi. So here this is basically the rest position. At the rest position, your displacement, your velocity, angular velocity, and your angular acceleration, both all three are 0. So if I displace this P from this position to this position, the angle turned by the cylinder is phi. So at this point, if you draw the component of the forces acting over this, it is your mg. Then you are having a, this is you are having component of this and component of this. Okay, let me draw this again. This is your mg, and this is your okay. Let me draw again. Suppose this is your configuration here, then you are having a, this is your mg here, and this is your two components. This is your phi, this is your mg cos phi, and this is your mg sin phi. So you can see here, when I displace this piston cylinder from this point to this point, then you are having a mg sin phi, which is the component of the force which will be trying to bring back the cylinder to the rest position. It means we are having a, this is your restoring force. So because of the restoring force available in the system, the cylinder will try to come to this position, and then it will again cross this point, will go to the other side, and in that way again you are having a same force here and will start oscillating about the rest position. So this is basically the condition here, and if in this, because of this, the system will be basically coming to the rest again at the rest position. So because of that, you can say here you are having some friction available in the environment and the air, and because of that the motion will keep on dying. and it is basically known as a die away motion. And because the system is coming to its original position after certain time period, it is known as a stable equilibrium. In the second condition, it is a neutral position here. So if I displace the piston cylinder from this point to this point, this is the displacement or the Peterson given here. So at this point, the system will basically move as a rigid body, moving from one point to other point, and the system will not have any restoring force here. Suppose here it is your mg here, and there is no restoring force in this direction. So because of that, this will remain here it is, and it will not come back to its original position. In the third one, so it is basically a neutral position. Every position is a equilibrium condition here, but you will not have any oscillation or vibration here. In the third case, this is your unstable configuration. If I displace it by phi, then this is your mg here, it become your again phi. This is your mg cos phi, and this is your mg sin phi. So here at this case again, if you say if I displace from this point to this point, the system will not come to the original rest position. Instead of this system, this cylinder will fly away. It will again move farther and farther position here, and in that way this is basically a fly away motion, and that's why it is a unstable equilibrium. So from this three figure, you can say very well that a system will vibrate or oscillate only if there is a restoring force. So for the all the mechanical systems which are having a vibration, you must have a restoring force. Now the important elements that constitute a mechanical vibrating system. Basically, we are having a mass, spring, and the damper as the major elements which constitute a mechanical system, which will be studied in the mechanical vibration. Besides that, you can have a external excitation force. So all these three plus this excitation force constitute a basic elements of mechanical vibratory system. Now it is assumed that all these three parameters are a constant quantity and do not vary with time. So here mass is basically a inertia element, and spring and the damper are the basically the restoring elements. Besides that, you will be having some initial input conditions. For example, at t is equal to 0, what is the velocity and what is the displacement that you also specify for a vibrating system. So in this case, the inertia element mass will basically store and release the kinetic energy. The spring element will store and release the potential energy. Kinetic energy for the mass is nothing but half m x dot square. X dot is basically velocity, and kinetic and potential energy of a spring is basically given by half kx square, and the damper, which is denoted by the c, is basically expressing the energy loss in a system in the form of dissipation of energy. So these three elements basically these three elements constitute are behave like this. These three elements have different excitation characteristics. Basically, a vibration can have two type of motion. First one is your linear motion. Second one is your angular motion. Linear motion is also known as a translatory motion, which is basically caused by the axial force, and this is basically caused by the torque or the moment. So all these three elements which I have described here will be having either a linear motion or will be having a motion angular motion here. So all the three elements will behave differently here. So for example, inertia elements, that is your mass, is characterized by the relationship between the applied force and applied force. Now basic applied force can be basically your linear force, or it can be a torque or a moment, and the corresponding acceleration response. That's why here you so that's why you are having a inertia elements will be having a half mass into F is equal to basically m F is equal to m into a, nothing but m x double dot, or it can also be equal to I alpha. I is the mass moment of inertia, alpha is the angular acceleration. This is your linear acceleration, and this is your mass here. So inertia elements are basically will be characterized by acceleration response. Stiffness elements are characterized by displacement one, like you can say half kx square or half k t into theta square. So basically k is the linear stiffness of the spring and kt is the torsional stiffness of the spring, which you already studied in your Stanton material, and x is the linear displacement and theta is the angular displacement. Similarly, your dissipation of the element by the damper is given by velocity response. It is given by half c x dot square. Half, sorry, it is basically half. It is not. So it is simply nothing but c dot into c into x dot. This is basically a dissipation of energy per cycle. So in that way, you will be having a three basic elements for any mechanical systems. Only the complexity of the system will be increased when you are having a very large mathematical model. Now let us come to the main reasons of the vibration. Number one, you are having a unbalanced centrifugal force. This force is because of non-uniform material distribution. Generally, we assume that density of the material is uniform all over. While this is not the case in real life, and density will vary from point to point, it may be a small variation, although because of that reasons you are going for wheel balancing of your automobile vehicles. Then you are having a second reason of vibration is every element of a mechanical system will be elastic in nature, and because of this nature vibrations are bound to come. In sometimes we are applying external excitation to the system. For examples, you are having a potholes on the road which basically act as external excitation and which and will generate the vibrations. Similarly, you are having a external excitation force in the form of periodic force, that is your F naught sine omega t, that basically also causes the vibrations. And sometimes wind will also cause the vibrations. For example, your electricity lines, telephone lines, etc. So these are the main reasons for a vibration in a system. Now, question arises, why? What is the importance of studying vibration in engineering? Number one, to avoid unnecessary or excessive stresses, which are basically caused because of the unbalanced forces and the vibrations. So generally, you have seen that when you are having a vibrations, you are having some displacement there or amplitude of the vibration, and that amplitude is nothing but it is basically a deflection in the elastic body, and the elastic body when they get deflected will generate the strain, and this will generate the stress. And because of, if so in the vibration study you are getting a stress in the system. So if we are having a large displacement or large amplitude of the vibration, then you are having a large amount of stresses in the system. So we need to avoid large stresses in the system. Number two, we are having a resonance conditions. This is the condition when you are having a very large displacement. I will discuss this in the next article. What is this? So at this point, your stress will be quite large and the complete mechanical system may fail. So we need to avoid the failure of the system because of vibrations and resonance. Then next factor is comfort level to the human beings. So human beings are involved in the universe here. So here we will like to give the comfort to the human beings. In your automobiles, your cars, we provide uh, comfort by minimizing the vibrations, and for that we use some elements in the cars. Then we need to check the vibrations. To analyze the vibrations, you need the vibration testing equipments, and to design this vibration testing equipments you have to study the vibrations. So for example, vibration testing equipments are there. Then you are having a musical instruments, hoppers and conveyors, which are uh, which are need to be designed, and for that purpose one has to study the vibrations. Now how you can uh, as you have seen that vibrations are beneficial as well as vibrations are detrimental for the human mankind. So we need to reduce or eliminate the vibrations. How one can do this? We have we so number one possibility is that if we remove the external excitation, it means if we make a roads uh, quite good, then we can remove the external excitation here, and then we can reduce the vibrations. Second and third point is using the shock absorber and dynamic absorbers that can also dissipate the vibration displacement and can give the comfort to the human beings. And the fourth point, if we are putting the system on some vibration isolator, it means if we put some rubber pad, they may act as a vibration isolator and that may reduce the vibrations. So these are the basically the reasons for the vibrations, importance to study the vibrations, and undesirable effect can be eliminated. The way you can do it has been discussed here. Now some important definition of mechanical vibrations, you already studied few of them, so I will be just going it very quickly. Number one, periodic motion. This is the motion which repeat itself after an equal interval of time. So this is your periodic motions, and this is repeating itself after certain interval time. Then you are having a time period is the time taken to complete one cycle. This is the one cycle here. Then frequency is the number of cycles undertaken by the motion per unit time. So you can say this is the period is given by 1 upon uh, uh, f frequency. Suppose omega is the circular frequency in radian per second, then your frequency in hertz or cycle per second is given by omega upon 2 pi, and time period is the inverse of this. Then you are having a simple harmonic motion. This is the spatial periodic motion, and it is defined by a particle moving on a circular path, and its projection to the diameter is known as a SHM. Here, particle is moving with a uniform velocity of omega 0. So it is given by x is equal to a sine omega t. You can have a velocity component by having a derivative with respect to t, a omega cos omega t, and this is your minus acceleration here. So you can also write this in this form. So here you can also write this x double dot plus omega square x is equal to 0. So generally you will use this equation in the free undamped vibrations, and the coefficient with the x or the displacement, this can also be theta. This can be theta double dot plus omega square is equal to 0. So the coefficient having theta of the theta or x is basically the square of the angular velocity of the system. So then you are having amplitude. It is the maximum displacement of the vibrating body from its mean position. This is the amplitude here. So basically this is the amplitude here, A. Then you are having a phase difference. Phase difference is basically the, if you are having a two rotating vector of the same frequency, having some angle difference between these two is known as a phase difference. This is your sine omega t, this is your omega t plus alpha. So alpha is the phase difference. So here you can say this is your x1, this is your x2, and this is basically a angle alpha here. Now the free vibration. So free means there is no external force. So when a system in the free vibration, when a system vibrates because of its elastic property. So suppose you are having a one spring and one mass here. So if I displace this mass by some displacement x and leave this as such, this is known as a free vibration, and there is no external force, there is no damping present here. In the force vibrations, I will be having some external periodic force. So if I apply a periodic force, that is your F naught sine omega t, then it become a force vibration. So in this force vibration condition, your frequency of the vibration omega, suppose this is your omega naught here, it becomes omega is equal to omega naught. So frequency of the vibration will be equal to the frequency of the forcing function. So in case you are having a free vibration, if I remove sorry, if I remove the mm, this force here, then the system will have some bit frequency, and it is known as basically omega n. So this is the frequency of the free undamped vibration of a system, and this frequency is basically a constant for a system. So for the km model, that is your spring mass model, your frequency omega n is given by square root of k upon m, and this is a constant value for a system. Then now come to the resonance. Suppose you are having a force vibration, and if this omega n is equal to omega 0, then this is the condition of resonance. It means it is the vibration of a system when the frequency of external excitation force is equal to the omega n of the system. At the resonance, you will study in the future classes, the amplitude of the vibrations are very large, and we should avoid the operation of the system and the machines at this condition, mainly because of the failure may occur suddenly. Now next is your damping. Damping is nothing but it is the resistance to the motion of the vibrating body, and damping is always present in a real system. It may be in the form of air drag and so on. Then you are having a viscous damping. This is the damping provided by the fluid friction, and this is the most frequently used damping in industry because it is simple to model. Critical damping, generally the viscous damping you will study in future classes, can be of three types. One is your under damping, second one is your critical damping, and third one is your over damping. So uh, in this three, critical damping is the minimum viscous damping. So basically in these three dampings you will be having a sometimes non-oscillatory motion, sometime oscillatory motion. It means you will be having a sometimes there will be a vibration and sometimes there will not be a vibrations. So for the critical damping and over damping, for these two conditions you will not have a vibration. They will simply follow a exponential decay of the amplitude uh, from over damping to critical damping. So critical damping is the minimum viscous damping that will allow to a display system to return to its original position without oscillation. Only under the case of under damping, you are having a vibration in a system. Then you are having a fundamental mode of vibration. Suppose you are having a 2-degree system. Suppose you are having a 2 degree of freedom of a system. In that case, you are having a 2 omega n, namely omega n1 and then omega n2. So out of these two, one will be lower than the other. In case of 3, you are having a 3 omega n. So you can arrange this in the ascending order, and the lowest omega n is known as fundamental mode of vibration. Degree of freedom, as you already know, it is the minimum number of independent coordinates which are required to specify the motion or the configuration of a system completely at any instant. So you can have a single degree system. This is your basically a KM model. So if I displace the mass by x, then you can find out the displacement in the spring, and you can find the all the forces acting on the system. Similarly, if you are having a simple pendulum here, if I displace it theta, only this is a one parameter, then you can specify everything and analyze the system. Similarly, you are having a crank mechanism. Again, theta is sufficient to describe the system completely. It is known as a single degree freedom system. Then you are having a 2-degree freedom system. Suppose you are having a mass resting on a two springs, and the two springs are having a different stiffness. So this system can be specified completely by one linear displacement and second angular displacement theta. Similarly, if you are having a two masses, K1 and K2, and M1 and M2 are the associated mass here, then you can displace these two masses by two x1 and x2 displacement, and then you are having a complete specification of the forces here. Similarly, this is the compound pendulum having a two simple pendulum. Again, you are having a 2 theta 1 and theta 2 here, and you can specify it completely. It is basically a 2-degree of freedom system. You can see here 2-degree of freedom system can have both linear motion, or it can be a both rotational motion. It can have a combined motion here. Then you are having a 3-degree system here. You are having a 3 spring and 3 masses. Then you are having a 2 springs, 3 springs, and 1 rotational component here. So you need to specify the 3 coordinates here for this. Generally, as you know, a body in the space can have 3 translatory displacements in xyz direction and 3 rotational displacement about the xyz direction. So a body in a space can have 6 degree of freedom, and if you consider each degree plus minus, it become a 12 degree of freedom for a system. Then you are having a infinite degree of freedom system. Suppose you are having a string. This is the string here. If you displace the spring transversely, then you may have this type of vibrations and displacement here. And to specify the displaced spring, you need to specify at every point, and so it become a infinite degree of freedom system. So here you can have, now next point is continuous and discrete system. If you are having a infinite degree of freedom like this, it is known as a continuous system, like cantilever beams, simply supported beams, string, torsional vibration of a shaft, and so on. While when you are having a finite degree of freedom, it is known as a discrete or lump system. So let us now this is all about your basically the terminology of the vibrations. Now let us come to the vector method representation of the simple harmonic motion, and I will be simply telling you the salient points of this one. Suppose this is your simple harmonic motion representation of a vector. X is the amplitude of the vibrations, and omega is the circular frequency in radian per second, and it is in counterclockwise sense. So here at t is equal to 0, x is equal to x naught. So this will basically lie in the epsica here. At T is equal to at t time, this is your omega t or is equal to theta here. So you are having a displacement is x is given by, this is your x here, the vector is having a x length here, is nothing but x sine omega t. Now if I make a derivative of this with respect to time, then you will be having, this is your x dot is equal to x omega into cos omega t, nothing but x omega sine omega t plus pi by 2. So this is your omega x time. Omega x is basically amplitude of the velocity, and it is given by this. And you can see here, this is basically having a pi by 2 phase lag. It is leading the displacement by 90°. This point is to be noted. So display velocity will always lead the displacement by pi by 2. Similarly, if you are having a acceleration here, it become x double dot is equal to minus x omega square cos omega t, nothing but minus x omega square sine omega t plus pi. So here you can see here acceleration is leading the displacement by 180°. So if you are having a displacement in the some direction, acceleration will always be 180° out of phase of the displacement. And you can see here the relative position of displacement, velocity vector and the acceleration vectors will remain pi by 2 and pi. Now one more thing is here, if omega is less than 1, then the amplitude of the velocity vector will be smaller and acceleration vector will be even smaller here. And the reverse is also true when omega is more than 1. Now let us come to the types of vibrations. So number one, you are having a free and force vibrations. I already explained this here. When there is no external force, it is known as a, and there is no damping, then it is known as a free vibrations. And when we are having a some external force here, it is known as a force vibrations. In the free vibrations, you can have simple pendulum as example. In the force vibrations, you can have a machine tools and electricity bell and so on. In the damp vibration, you will be having a damping element there. And because of this damping, your amplitude of the vibration for every cycle will decrease continuously. And because of that reason, the vibration will come to its standstill position after certain time. In the undamped vibrations, there is no damping element, and so you will be having a constant amplitude of the vibrations, and this is the ideal conditions for vibrations which will not exist in real life. Then you are having a steady state vibrations and transient vibrations. This is again the same thing of as earlier. In the ideal condition, it is again the basically the free vibrations, and the amplitude of the vibrations will be same for every cycle as there is no damping. While in the real systems, the amplitude of the vibration will decay continuously like this, and they will vanish ultimately. This is known as basically a transient vibrations. Then you are having a linear and non-linear vibration. A equation of motion of a single degree of freedom system having all the four components mass, damping, spring, and external force is given by this equation. The first one is known as a inertia force, second one is known as a damping force, and this is known as a spring force. If all these three forces are linear function of acceleration, velocity, and displacement, then it is known as a linear vibration. And the law of superposition is valid only for this system. In the case of nonlinear vibration, these three forces will not be a linear function of their displacements. Like this is not a linear function of acceleration, not linear function of velocity, not linear function of displacement here. So in this case, suppose your spring force is given by this. Here it is a function of kx plus x cube. It is basically a non-linear with respect to displacement. So it become a non-linear vibrations. And you will not have law of superposition for this type of vibrations. In this, suppose spring is given by this. If x is very small, then it is basically approximately equal to kx. It means for a small amplitude of the vibration, all the system will behave like a linear vibrations. And if you increase the amplitude, then this factor will be dominating one and it become a non-linear vibrations. So you can say linear vibration become non-linear when you are having a large amplitude of vibrations. And it is because of this reason in your yesterday experiments, if you displace the pendulum too much, it become a non-linear vibrations. That's why you have to keep the pendulum displacement small. Then you are having a deterministic and random vibrations. If you are if this force component in a system is predetermined, if you can determine this forcing function in the vibration, it is known as a deterministic vibrations. If this is not deterministic type, it become a random vibrations. So we are having a altogether a different course for random vibrations where we use the statistical tool to analyze the vibrations. Then we can have longitudinal, transverse, and torsional vibration. So in all the three, you are having a shaft. So if you hammer this, but this is your equilibrium position. B represents the equilibrium position here. And if I put a hammer on this side, then the shaft will start vibrating up and down. This is your longitudinal vibration. This is known as basically a longitudinal axis. So if the system vibrates longitudinally, it is known as a longitudinal vibrations. Now, if I put a hammer in the transverse direction, then your system will vibrate like this. This is known as a transverse vibrations. Now, if I make a disturbance in a clockwise sense here, theta, then your system will vibrate in the torsional way like this. It is known as a torsional vibration. So this is all about this class. So I have basically covered all the basic concept of the vibrations and will cover some more in the next class. You can have questions on anything as we discussed here. Mukul,
Yes, sir. Yes, sir.
anything? Anybody want to ask anything here?
If anybody have doubt, he can ask, he or she can ask.
Oh yeah.
सर आई वांटेड टू आस्क कि ये जो आपने अभी करवाई है पीपीटी से,
हम्म।
सर आप ये प्रोवाइड भी करोगे हमें?
मैं ऐसे ही मतलब जैसे मैंने किया इतना करूंगा रिकॉर्डिंग इसकी।
अच्छा, आप ऐसे पूरी पीपीटी नहीं दोगे?
We
मतलब
will
रिकॉर्डिंग,
provide you the recording
रिकॉर्डिंग,
of this lecture,
रिकॉर्डिंग
but
ऑफ
not the
रिकॉर्डिंग।
PDF. Though PDF,
Yeah.
this PDF, we will
It is
not provide
already
you.
in the books basically. Okay. I have
ओके सर,
concise this. Okay. हाँ.
You can refer PK Grover and Ambekar book for
Ambedkar book
mechanical
for,
vibration,
yeah,
as
yeah,
told by Mangal sir.
ओके
Okay,
सर,
so this PPT is prepared by both of these books. So you have
yeah.
to refer both of the
Be-
books.
It is beside this book, I am having my teaching experience of this course since
Yes,
last
sir.
15 years, 15 years. So I am having some component in that. Okay.
यस सर,
Yeah.
So you must go through the lectures as well.
यस सर,
Okay. Okay. I will continue with some more basic concepts in the next class, and I will like to cover this subject, this first topic in 2 or 3 classes itself. And you may have your first assignment by next week on these topics. Okay, so one more thing I forget yesterday, and the thing is that I will not take any repeat test. If you miss any quiz, all right, if you miss any midterm examination, I will not take retest. So you absent from any test at your own risk. All right, students.
Yes, sir.
Okay, okay,
Yes,
we will meet again in the coming Monday for the second class.
yes, sir.
Okay,